Okay, so you're welcome back. So today or now we are going to look at buck converter or buck regulator. Okay, let's say we have buck regulator. Now remember, a buck regulator is it's a step down converter. It steps down DC voltage, all right, from a specific value to another value, all right. So we are going to look at a sketch of a buck converter, and then from there we check how it works. All right, so if we have like that, this is a typical sketch, all right, of a buck converter. Now this is a buck converter this is our diode here. We have our inductor there. We have our VS, the source voltage there. And then we have our load, and remember the voltage output here is our VO, right? Okay, so now let's see how a buck converter works. Now, remember that we want to turn this on and off, all right? Now, when time is on, let's see, if you on this, now you are going to have this will look like that. Current cannot flow through here because this will reverse bias, so you have that. Okay, you have like this, right? You can complete the load, can have the load, but we just want to see what happens when you turn this on. Current flows like that, right? Into this. Once it's fully charged, then it will discharge into the load, all right, to the load there. Okay, so now it means that as this time is on, at time on, we are going to have a current being built up. Remember that an inductor builds up current. So as current flows through here, the current will be building up. Okay? All right. So the current you're going to see here will start building up. Now, immediately you turn it off. Immediately you turn it off, in other words, you open this. If you open this, right, now remember, this has built up current, isn't it? Now, and there's going to be a voltage across that inductor because of the current induced. So now, in other words, now we are going to see only this, because it is open, you will now see only that. So you have like this. Okay, remember, I can just put like that. If you want to put a diode, it's fine. But what I'm saying, that current will flow like that. So now that current that was built up is now going to do what? To discharge. Okay. All right. So in other words, now we're going to have this current that builds up is going to discharge. Because remember, we have our load there. Okay, so this will now be like a typical equivalent circuit. Remember, this side is closed. I mean, here is open, so you don't see anything there because it's open. So we're only looking at that, what is happening here. So you're going to have a voltage here on the inductor. You have a voltage there on that inductor. But what I'm saying is that immediately you close this, the current flows through here. So there's going to be a current build up. And once you open it, that voltage, you have the voltage here, the current that was built up will be discharged, right? Okay, through this diode, all right? Because it's like a short, so it will be discharged like that. So you're going to have, so immediately you turn on, you turn off, current, that's how the current will be going, all right? Current through this inductor will be going up, down, up, down. So you will get something that looks like that, up, down, depending, okay, on your time of on and the time of off. Okay, so now what we do is we are going to use that scenario, okay, to derive the equation, the duty cycle equation for a buck converter. Okay, for us, before we do that, remember that at time of on, let's just look at what happens. This voltage here is our Vs, right? You have there as your Vs. This is your VL. Agreed? So, and this is your output voltage across this and that. Okay, is your VO. So just if I use Kirchhoff's law, this voltage here, Vs, is the same thing as voltage VL plus VO, like that, right? So it means that VL, this is as time of on, VL is the same thing as saying Vs minus VO, just at time of on. At time of off, when you look at that at time of off, now, we only have this, there is no Vs here, all right? So in other words, our Vs equal to 0. So 0, there's no Vs. So this Vs equal to 0 equal to this plus VO, because now there's nothing here. So 0 equals to this plus that voltage across here, which is your VO. That means that VL is minus VO. You get it? So now we are going to now use this, okay, to derive an equation. So for a buck regulator, now look at what happens. Remember that the voltage across the inductor, this voltage across the inductor, how do you get a voltage across the inductor? We say is L di dt. If you remember the voltage across the inductor is L di dt, right? Okay, so it means that we can write like this: L VL equals L change in I divided by change in time, like that. So if I have this, because now I've seen here that there is going to be changes. Look at the time here is our time on, and time here is time off. So there will be a change in time. The change in time for on will be different from change in time for off. So what I'm going to do now first is, let's write the change in current, because now here, this builds up and that comes down. So that means that there will be a change in current. So there will be a change in current here, there will be a change in time, so we'll have that. So the first now we'll do is, let's make change in current subject formula first, okay? So that you have this to be VL delta T, VL delta T over L. This is our change in time, in current, right? And we said that this builds up, time of on comes down, time of off, on like that, on like that. Do you know that from here to here, that is from here to here, is our change in I? Okay, that's a change in I from this point to that point. If I want to get the average value will be this, but the change in time will be between this point and that point, right? So you can see that the delta I rise is the same thing as delta I fall, but in negative direction. Okay, so if I write delta I rise, because this is delta I rise, this is I rise, this is I fall. Delta I rise is the same thing as delta I fall, but now in negative direction. Okay, so now, why do I write this? Because now I know that my delta I is VL delta T divided by L. Now, for time of on, delta T is T on. For time of off, delta T is T off. Okay? So, now, I'm going to use this now with these two scenarios and derive an equation. Let's look at it. Delta I rise. Delta I, remember, we should know this very well. Delta I is VL delta T over that. So, I'm going to write VL. What is a VL for rise? Remember, this is for our rise, and this is our fall, right? What is a VL for rise? Look at it, VL. VL is Vs minus VO. So I'm going to write that here, Vs minus Vo, okay, into, what is the time? Which time are we talking about? Time of on, all right, into T on by time of on. Now, time of on divided by L, that is for rise. I say it's the same thing as, now the time of fall, so delta I fall, now I will just say, okay, delta I fall. Now let's substitute what is the voltage on the inductor at the time of fall. Look at it, it's minus VO, so I have minus VO. Which time is that? Is time off. Okay, now divide by L. So remember that this L, we take out that L, so that you only have Vs minus Vo into time of on equals minus Vo by time of off. Did you get that? And we know also that time of off is the same thing as period minus time of on. Okay? Did you get it? Just check the time. All right, so it means that we can even substitute the values. We can, because I need to eliminate the time of on, okay, and the time of off. From what we did previously, if you check our previous videos, remember when we were looking at a duty cycle, we said, okay, that time of on over period, Vs equals to Vo, where this is your duty cycle. In other words, we say duty cycle K is the same thing as T on over T. That means T on is what? KT, right? T on is KT, isn't it? So whenever you see T on, you put KT. Well, what will be T off? T off will be 1 minus K T, right? So remember, here is T on. So even what is it called? T on is that. T off also is 1 minus K T. Okay, you can just check it. Remember that T off is T minus time of on. Okay. All right. So now that means I can put here as KT, right? Time of on can be written as KT. So KT Vs minus Vo, like that, KT equals minus Vo. This is 1 minus KT. Right? So please, you need to expand this. This is Vs minus Vo times KT, which is our T on, equals minus Vo by 1 minus K by T. Now, you can expand that. When you expand this, you are going to get and do your elimination method. So you get Vsk. So you get Vsk minus Vo. Okay, just expand it. Let's see, so that we don't have. Let's say we have, this is Vsk. Remember that this is T is here, T is there. Let's remove out the T first so that we don't create problem, because this is the same. Divide all through by T. So that we only have Vsk minus Vok equal to minus Vo, right, plus Vok, like that. Okay. So that you can just collect your like terms. Okay. So when you collect your like terms, at the end of the day, you will get that K is Vo over Vs. All right. Remember, this is a Vok. You take that one, this one here. Okay. Now with that, now you are going to get that at the end of the day that K is Vo over Vs. So please just try it. The basic thing for you to know is how to derive this. Because I can ask you to derive this, okay, to prove that for a buck converter, that the duty cycle is VO all over VS. Okay? All right, then you should be able to derive that. Okay, thank you very much. In the next class, we're going to look at another derivation. All right, but remember, just know this very well, what I have sketched here. All right, now this is how the current will look like on the inductor. Current across it, flowing through this inductor, going up, down, up, down. At the time of on, this is at the time of on, and this one is at the time of off, on, off, just like that. Okay, but what about if you are asked to sketch the voltage? How would the voltage look like? Let's just finish up that so that we see how would the voltage look like. Let's see. Remember we said the voltage across the inductor. How will it look like? The first thing, what is it? We said, look at this, Vs minus Vo. So if we have time of on here, the voltage inductor Vs minus Vo, when the switch is on, the voltage will be Vs minus Vo. But when the switch is off, the voltage will be minus Vo, right? When the switch is off, minus Vo, like that. Okay. So time is on, time is off. Time is on, time is off, just like that. So if I sketch something like this and say that this is for a buck converter, if I put whatever, let's say minus 20 volts here, it means that this 20 volts is the output voltage of the buck converter. So how much I put here, if I say this is 50, so you know that this 50 is Vs minus Vo. So that if I know Vo as minus 20, then I can easily calculate the source voltage. Okay? All right. So that, look at it now. This is the voltage across the inductor. So that if we want to get now the current flowing across the inductor, okay, IL. Now, remember we said at the time of on, what happens to the current? The current builds up. At the time of off, it goes down. On, like that. It goes like that. Okay? All right? So that if I get the average value of this, the average value of this signal will give you the output current. Because we know that for what is it called? For a buck regulator, with our sketch that we had, remember that current flowing through here, this is a diode there. Now, and this is our capacitor, our load. So current flowing through here is same as the output current, I.O. So how much you get there is the average value of that current that is going up, down, okay? So the average value here is I.O. Why from here to here, if I check this distance and that distance, we call it ripple. So delta I is ripple current. Okay, did you get it? All right, so you should try, okay, to understand what is going on here. All right, see you next time. Thank you very much.